Alright, hello, I'm James Trapp.
I'm Javier Rosas.
And this is the excavator final report redo. It's getting sent with the completed design and functional robot. So to start off, just as we stated before, I primarily worked on the physical model while Javier did some helping out, especially with the electronics and the code, while Javier did most of the work with the Simulink file and Simulink modeling, while I did quite a bit with the creation of the XML files and some odds and ends for helping edit the Simulink model. So to start out, we have our CAD model. It's the same. We used SolidWorks and Simulink to create the digital model for the excavator. We'll talk about Simulink in a bit. The SolidWorks file we got from an open source website, Thingiverse. Then we modified it by adding in the 4-bar mechanisms so we could use rotational motion as opposed to translational motion through the use of a hydraulic, because hydraulics are too expensive for us to do for this project. So some difficulties that we had, we didn't really have that many for using SolidWorks. We had quite a few more with exporting the file to an XML. I think we talked about this before. We needed to download a free trial of MATLAB, so we would have admin privileges, so we could then download the plugin for SolidWorks through MATLAB. It wasn't difficult, but it was very time consuming compared to what we were expecting.
So here's our original simulated model. It was a bit more accurate to what we have as our physical model. However, it became more complex to edit and understand the data. As we were starting to put in spring stiffness and damping coefficients and messing with equilibrium positions, we just found that we could not find a way to anticipate what we could get or understand what data we were able to get. And here's our original block diagram with all the sensors and revolutes involved. And here's our final simulated model. We just have our three revolutes with our boom, our stick, and our buckets. It was less complex, fewer parts. We were better able to modify the motion and understand what data we got and interpret what we have, rather than just kind of shooting in the dark with numbers that we would input. And here are our final numbers for our simulated model. Our equilibrium positions, we were able to determine we were able to understand how those positions changed based upon what numbers we inputted, and so that just gave us our starting positions for the model. Spring stiffness, we attribute most of that to our motors. On this boom, we have a rubber band that helps alleviate tension. Additionally, on the stick, we added an additional rubber band to help with any movement. And then the bucket is more free flowing, which has is the reason why it has no spring stiffness. And as far as damping coefficients are concerned, once again, the motors are going to be helped there to create any friction or keep the object still and not move.
Yeah, so the dampening coefficient that we have We chose incredibly high ones for both the stick and the bucket because the friction within the motors themselves cause it to not be able to freely rotate. We chose a relatively low one for the boom because it was a lot easier to manipulate. It was more precariously balanced with the elastic tubing and the weight of the entire arm. So the dampening coefficient didn't seem as if it was that great compared to what the spring force was or what the motor was impacting, or how the motor was impacting the system.
Here's our final simulated model block diagram. We also have our electrical subsystem included in here, along with our sensors. And our sensors are going to be measuring the position, the velocity, and the torque. And the torque should be directly related to what current we're inputting from the electrical subsystem.
So it should be noted that for our electrical subsystem, it oscillates because we decided to use an AC current so that we could input a sine wave. We wanted to do this so we could see the difference between what the motor is doing at its peak up and peak down without doing separate simulations. This was just a way that we did this to make it easier on ourselves. There's not really any other reason than that, so that's what the data will reflect. So we had a few issues with Simulink. Primarily it was with the complexity of the model and with the creation of XML files. Other than that, we haven't had any new issues since what we reported to you before. So for the physical model, this again is the original one with the DC motors, the Arduino Uno, the H-bridges, and the battery pack. As we discussed before, the motors weren't powerful enough, so we moved on to what is now the final design. So it's the same physical model as before. It's got all of the same 3D printed components. The only real changes are the voltage source and the servo motors. The Arduino is used in a different way than it was before because we don't need to have a left and right output. It's just a single output because these are servos. For the voltage source, instead of using a battery pack, we spliced open a USB cable and had that operating from a wall outlet through an AC to 5-volt converter, which is just a standard cell phone charger. And the servos themselves, through the code, we provided the angle at which the servo would drive to, and that's what you're seeing here. So the difficulties we've been having, they were the same as before, except now with the servos there's a new one. Because we are powering all 3 of the servos in parallel, when we attempted testing the current with the ammeter, we were not able to get any data that was useful because just by using the ammeter we were significantly lowering the amount of we were significantly raising the amount of resistance on that particular part of the parallel circuit, which lowered the amount of current that was going through that portion. So while testing with the ammeter, we were not able to get data where we would also have the servos moving, and the current would display at something around 0 because there was not much going through at all.
So here's our data collected through our through Simulink. So our first graph shows our position, our second graph shows our velocity, and the third graph shows a torque. The position starts off, and that's when it starts off at a negative number that's going to just correlate with the equilibrium position, and it slowly decreases over the time, and that just has to do with the position that the boom is going to end up at. Velocity is fairly consistent across, and the torque is going to start off at negative 600, since that was the supplied current that we gave the joints.
So as you can see throughout both this Revolute, Revolute 2, and Revolute 3, all of them seem to follow a very consistent path, following the input torque very closely. Again, as I stated before, we are using an AC current so that we could get this variability in the design itself. So for the data that we collected from the physical model, we were supplying it with a 4.8 voltage. The bucket was moving with a change of 70 degrees on the servo, the boom with a change in 50 degrees, and the stick with a change in 75 degrees. We were able to both see this by lining up a protractor against the servos as we individually move them, as well as just seeing from the code that we designed, we haven't changed those degree measurements. The protractor business was mostly just to confirm those numbers. With the velocities, we were able to get 112.9 degrees per second, 41.32 degrees per second, and 101.35 degrees per second for each of the individual parts of the robot. The method that we used to get this data was we timed how long it took to change the 70 degrees and then converted it to degrees per second.
These velocities can be attributed to the weight that each object is having to carry. So the boom is going to be at the base. It's going to be lifting the stick and the bucket. The stick is in the middle, which is only worrying about the bucket, and the bucket is not going to have any weight, which means it's going to have the highest angular velocity.
So there's a few things that we can talk about here with the difference between the data that we collected and the data that we modeled. One of the first things that we can say is a big difference is that in the data that we modeled, we were able to change each joint individually. For the servos, you only supply them with the degree that they drive to, and then they drive to that. So each servo takes the exact same amount of power. A second thing that we noticed as a big difference between them is that we had significantly higher amperage in the data that we collected in the model, and we determined, or we believe that this is due to the fact that the servos have a significantly higher torque ratio than we accounted for. Looking at the internal gearing, it looks as if they have somewhere along the lines of 100 to 300 to 1 ratio between the actual electrical input and the output that is on the stick.